today what we will do is we will look at planar graphs. Planar graphs, and this is part 1 of the series. This is part 1. So let's get started with a smile on our face and let's begin. So first we will look at the basic definition of planar graphs. Okay. So the graphs, suppose I'll make an example of a graph on 4 vertices, 1, 2, 3, 4. This is the K4 complete graph on 4 vertices. Okay. And what we have to do to test that whether this graph is planar or not, what we have to do, we make on a sheet of paper or on a plain surface the edges such that no two edges cross each other or intersect each other. That means I have to redraw this graph. This is same as what I can do. I can see no other edges are crossing each other, only these diagonal edges are crossing. So we have to redraw them in such a way on a sheet of paper that they don't cross each other. Can we do that? Let's see. So these are not intersecting, so these are okay. 1, 2, 3, 4, and this is fine. Now what about this second edge 2, 4? So what we can do, we can connect, cause in graph what is important is connectivity between the nodes. I can make this straight line like a curved line as well. That does not matter. What matters is which two nodes are connected. See, here also 2, 4 is connected. Here also 2, 4 is connected. So these two graphs are isomorphic or same. Their connectivity is same. So um, this K4 is planar. Okay, so we have to be always careful with the basic definition because sometimes the questions confuse us. For example, this question, you also guys can pause the video and think about it. Is a tree planar or non-planar? This is the question. So how do you understand whether tree is planar or not? For simple small questions to check whether a graph is planar or not means, can you draw a tree? Tree means which is connected and acyclic. Acyclic means no cycles, and connected means you can reach any two vertex x and y of the graph. There is a path, always a path between two edges. Okay, so I will make an example of a tree. Let us take this example. So this is the example of a tree. Okay, 1, 2, 3, 4, 5, 6 on 6 vertices. So are the edges crossing each other? No, there is no cycle and no edge will cross each other. So yes, tree is a planar graph. Tree is planar. That means we can draw it on a sheet of paper with no edges crossing each other. Okay. Now why is even discussing planar graphs important? I also used to think like that. Why we are reading planar graphs? Why is it even important? So let us see the analogy and where one of the applications where this planar graphs information can be helpful. So there is a situation that we have three houses. Three house and three utilities problem. This problem is called. We have three houses. This is house 1, house 2, house 3, and we have three utilities or three types of connections that the houses need to be made. First is water supply connection. This is water supply connection, W1. Then is your electricity connection. I will write it as short form E1. And next is telephone line connection, T1. So what we have to do is, the question is, all the three water, electricity and telephone line connections has to be made from the houses, powerhouses, to to these three houses. Okay, and we don't want such a complicated graph that where the edges, the lines or the pipelines and the electricity lines or the water lines and telephone lines are all jumbled up. We don't want them to be intersecting. We want them to be non-intersecting and very clear to maintain and easy to identify. If there is some fault in, say, the water supply, wait, I erase this part. Okay. If there is a false fault in, suppose, the water pipeline, then I should be able to separately work on it, identify which is the water pipeline, and I can work on it without any difficulty. That is the benefit of drawing a planar graph. So the question is, can we draw the connections for each of the houses? I will draw the connections with a different color. Okay, so okay, and white. Okay, so this looks very jumbled up, isn't it? So in order to, for this network or this graph to be more easily maintainable, easily repairable, है ना? What we want is all the edges or connections of the three houses to be not intersecting, no intersections. Can we do this? This is the question we are asking. And this graph is called K33 because we have three, this set, houses set, they don't have connections between the houses, and this supplies or the utilities part also, they don't have connections in between them, but they have only connections across these two sets. Okay, so this is known as complete graph on three vertices. So is this planar? This is a question that the people who want to create or connect these connections might ask. We will see the answer to this at the end. Okay, next go to the next theorem, that is Euler's formula. So is there any test, or how do we understand from looking at the graph, can we make it planar or not? Can we rearrange the edges in such a way that the edges don't cross each other? So for testing that, there is one condition, but this is a necessary condition but not sufficient condition. Okay, I will tell you what that means, and this is called the Euler's formula. Question is litmus test. Is a graph planar or not? A graph planar. How do we know that? Okay, the first thing that you can use to test is Euler's formula. Euler's formula that says if a graph is planar, then definitely this condition will hold too. That is the number of vertices. I am representing it using V minus the edges plus the regions which are enclosed by the edges, by the cycles, should be equal to 2 always. And this is true for connected graphs. Okay, connected simple graphs. So if a graph, if some graph is not, uh, for some graph this condition is not true, then definitely we can conclude that the graph is not planar. That is known as the necessary condition. But if some graph is satisfying this condition, then we need to do more tests. That is not sufficient to definitely come to the conclusion that graph is planar. Okay, so we have more tests for that. Okay, now let us see the induction proof that for any planar graph, this Euler's formula is definitely true. How do we prove this? Okay, go to the next page. Let us draw the first graph that I made, that a K4 graph, complete graph on 4 vertices. Okay, I will level the graph A, B, C, D. Okay. So, how many vertices we have? Vertices we have 4. How many edges we have over here? 1, 2, 3, 4, 5, 6. Edges are 6. How many regions are there? Let's redraw this graph in a planar fashion. Okay, A to C and B to D. So A, B, C, D. Okay. So how many regions can you see over here created by this planar graph? 1, 2, and 3, right? So regions are 3. So let us see this condition is being satisfied or not. Okay. So vertices 4 minus edges 6 plus 3. How much is this? 4 minus 6, that is minus 2 plus 3. Oh, wait. There is one more region. 1, 2, 3, and this outside this part. That is 4 regions. Regions would be 4. Yeah, the regions would be 4. Sorry for this. Because see, we have this triangle 1 region, this second triangle number 2 as second region. This between inside this AC edge, this is the third region, and fourth is outside this black part. So there are 4 regions. So this not will not be 3, this would be 4. Okay, so 8 minus 6, that is 2. So this is being satisfied. Okay, now how do we prove this using induction? Okay, we will assume that this theorem is true for any k vertices, v vertices. For v vertices, this is true. Okay, wait, with an eraser. What we will do for a graph having v vertices and e edges and r regions, we will assume that this condition v minus e plus r is equals to 2 is true. We will assume that. Okay. Now what we will do, we will add one more vertex to this graph, and I know this graph is connected. Okay, so for this graph to be connected, if I add one more edge now E, what I have to do, if I add one more vertex E, I have to add at least one edge so that this graph remains connected, because we are proving this for simple connected graphs. Okay, so what happened, I added one edge. Okay, I will erase the above part. Here I will erase. Okay. So what I did is, I will change the color. I added one edge E, correct? I added one vertex E. I added one edge DE. So in this formula, what we happened, the vertices has become V plus 1. The edges has become E plus 1. Okay, and the regions are same. See, the regions has not increased. Okay, so regions is R only. So this plus 1 and this minus 1, they cancel each other out, and this value is still 2. Okay, now what I do is I try to increase the regions and I don't increase I remove that extra edge. Okay. 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 I removed that extra edge, that extra vertex. Okay. Now we try to increase the regions. How can we do that? Okay. What we do is we try to increase the regions, right? If we increase the region by 1, the edges will also increase by 1. How can we do that? In this graph only we introduce one more edge. Okay, so let's continue that the intuition, how the researchers came that for a connected simple planar graph, this Euler's formula is valid. Okay, so first we saw that if you introduce for a graph, if this, we will assume that this Euler's formula holds true, and then we introduced one extra vertex and one extra edge. When we introduced one extra vertex, and then one edge was also introduced, and this plus 1 and minus 1, this made this Euler's formula's value constant. Now we will see another example, because in this complete graph there is all the edges are already there. So what I want to do is that we will introduce one extra edge to increase the region, okay, without introducing the number of increasing the number of vertices. Then also, cause there will be one extra region and one extra edge, so these two will be cancelled out, and again our this constant value holds true, okay, in general. So we will see another example where all the edges in the graph are not present, it's not complete. Okay, we will see this house graph. Okay, this is the house graph. Now we will number the vertices: 1, 2, 3, 4, 5, 6. Okay. Now, what are the number of vertices? Let's see. 6. Number of edges: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 edges. Regions: 1, 2, 3. Regions are 3. Okay. Now what I will do, we will join one edge, increase one edge, and we will assume that for this graph, the Euler's formula V minus E plus R is equals to 2. This holds true. Okay. Then we will introduce one extra edge to increase the number of regions. So from 3, now this the regions has become 4. Okay. So we have the vertices are same. We have not changed the vertices. We have increased one edge. We have increased one region, that increased one region, and this plus minus 1 and plus 1 would cancel, and again this value will become constant 2. So this gives us a feel that yes, this Euler's formula holds true for any connected simple planar graph. Okay, but this is not sufficient. We will see an example, two famous non-planar graphs K33 and K5, that satisfy for those Euler's formula is true. It will come out to be 2, but still they are non-planar. For that we will see another inequality. Okay. Yes. So let us make a sample graph. Okay. Uh, this is our graph. Let's make it like this. Okay. 1, 2, 3. Regions 1 and 2. There are two regions in this. Okay. So we can see in minimum how many edges are required to enclose a region. This is a region, closed cycle. So minimum smallest cycle has 3 edges, right? So I know that 3 times R, right? Every region will have 3 edges. So 3 times R means 3 times the number of edges means we are counting every region how many edges are used to enclose the region. This is less than actually our graph how many edges it has. Okay, suppose there were 2 cycles in this, and one was a 3 cycle, another was a 4 cycle, right? So actually the number of edges which are actual, number of actual edges will be more than this. If we assume that all cycles are 3 in length, that would be greater than this. But if, let's see, every edge, see, I will make another cycle over here. Okay, 1, 2, like this. Okay, so 1, 2, 3. Still we have 3 regions. Okay, so look over here. This edge is counted twice in every region. So if we assume every cycle, for every cycle, all the edges are counted twice. Let us assume that. Okay, all the edges are counted twice. But see, actually this edge is counted only once. It is not being counted twice. So this would be more then twice the number of edges for each the region. So what we can say is this inequality hold true for any simple connected planar graph. 3r is less than equal to 2e. But this condition, if this some graph, connected simple graph, is satisfying, not satisfying this condition, this is coming false, then definitely you can conclude that graph is non-planar. This is called the necessary condition. But if some graph is satisfying, for some graph this inequality is coming to be true, then you cannot directly jump to the conclusion that this is definitely going to be a planar graph. Okay, so you have to do more tests. The full proof test is known as Kuratowski's theorem. Okay, so these two planar graphs, non-planar graphs, these are two famous non-planar graphs. One is K5, 1, 2, 3, 4, 5. This is a complete graph on 5 vertices. Okay. Yeah. So this is a complete graph of 5 vertices. This is non-planar and we will see the proof of this. Okay. First, I will tell you what is Kuratowski's theorem. Okay. I don't know the spelling of it. And another is K33, which we saw in the application of the 3 utilities and 3 houses problem. Okay. There would be edge between the two sets. Okay. Pause the video and try to make these graphs on a sheet of paper with no edges crossing each other and see if you can come up with a solution. Don't try too hard because you will not be able to draw it on a sheet of paper. There, if you want to draw it on a sheet of paper, always some edges will have to cross each other. Okay. So this is K33. So any graph, Kuratowski's theorem says that any graph, if it is homomorphic to either K5 or K33, then it is definitely, you can conclude it is non-planar. Cause these two famous non-planar graphs cannot be drawn on a sheet of paper with no edges crossing each other. Okay, what is the meaning of homomorphic? Let us see in easy terms. Okay, so suppose what I do is in in this graph only the edges. This is an edge 1, 5. What I do, I introduce one more vertex over here. So what happened? Original connection was 1, 5. What I did, I added one pit stop over here, or we can say that you had, there was a road connecting 1 to 5 and you introduced one, what do you say, in between the start and the destination, final destination, there is one stop for drinking, for doing some activity. But essentially the structure of this graph having subdivisions of degree 2. Okay, this is degree 2 means the this vertex is not adding any new edge connections, because in a graph the important information is which two nodes are being connected, but this extra node is not adding any new information in the structure. So we can say the graph with this extra 2 degree vertex named as A is not adding any new structure information. So these two graphs are structurally same or homomorphic. Okay. So if any, by introducing any new subdivision degree 2 vertices in between the edges, okay, or making subdivisions to the original k5 or k33 graphs, then if you remove these subdivisions of degree 2 and join the edges directly, if it results in k5 or k33, then the graph we can conclude is definitely non-planar. Okay. So this is suppose a B, this is C, this is D, this is E, and what you do is you you have redrawn this. We'll erase the remaining things. Okay. Okay. And what I do is I redraw it a little bit like this. Wait, this is E, right? E, then this one, this is two, this is D, this is three, this is C, 4, then again will name is F. Okay, from 4 there is F, then there is 5. From 5 there is in between 2, like this. Now this graph is looking very different, but actually these two graphs will be same. See, I'm adding these connections also. 1 to 3, 1 to 3, 1 to 3, 3 to 5, then 2 to 5, 2 to 5, then 1 to 3 I have added, 1 to 4 I have to add, 1 3, 1 4, 1 2, okay. Then from 2 we have to add. Okay, let's continue again. So, what is homomorphic graph? Actually, if you get a graph which does not look like K5, okay, so see, I was making by adding more vertices, like dividing the edges by adding 2 degree vertices, that was not adding any extra information about new edges or new connections between two nodes. So this extra information can be removed. Structurally both the graphs are same, but it does look a little different. So I was redrawing the edges again, the remaining edges, right? 2 5, I connected 2 to 5, then 2 to 4, then 3 to 1, 3 to 5, 3 to 1, 3 to 5. Okay, yeah, all the edges have been drawn. See, these two graphs, they look geometrically, structurally different. But what you do, you flatten the vertices. I will draw it with blue. You remove this vertex E and flatten the vertices. It will look exactly struck the same as K5, like this. See? And you remove this E, erase this E, these subdivisions. So both the graphs, this type of similar in structure, basic structure is called homomorphic graphs. Okay. So any graph, if on removing 2 degree vertices from edges, they are not adding any extra information, you get again a K5, then it is definitely non-planar. Okay, similar thing stands for K33 as well. Okay, so let us move on to another inequality. Okay, that is necessary but not sufficient for a graph to be planar. Okay, so we will use the Euler's formula V minus E plus R is equals to 2. Always remember this is true only for connected simple graphs. This is not true for disconnected graphs. Okay. Now another inequality we saw, 3r is less than equal to 2e. Okay, we will use this to create another inequality. Okay, I will write it small r. These two variables are same, small r, and this is small e. Okay, so we'll write small e. Okay, now what we will do, we will remove r from this formula. Why we are doing this? Because counting regions in a complicated graphs will be difficult, and drawing it, trying to make all the edges non-intersecting would be very difficult. So what we do, we write r less than equal to 2e by 3, and we substitute, we remove this variable r in terms of e. So I know that in the, see how do you introduce the inequality over here? This side is equal to this only when this value is equal to r. Now something is greater than r. So if you add something which is greater than r, so this side will become greater, right? So v minus e plus, if I write 2e by 3, then this side is greater than r. So this addition would become greater than 2, greater than equal to 2. Okay, be careful at this place. Okay, now if we, I will remove the above what I have written over here. Okay, I hope you understood how this came. Now what we do, we take LCM, 3v minus 3e plus 2e greater than equal to 2 3 is 6. Okay, this implies 3v minus e greater than equal to 6, or e, we will bring e, add e on both the sides, okay, and subtract 6. Okay, so yeah, so this side would be, this side would be 3v minus 6 is greater than equal to e, or e less than equal to 3v minus 6. Okay, all right. So this is it for this video. Now we will see in the part 2 the proof how K5 and K33 are definitely non-planar. Okay, if you like this video, please share it with your friends and subscribe to my channel. And happy learning, and keep exploring more applications of planar graphs. Okay, bye bye friends.